Okay.
Hello.
Hi, I'm just hitting some buttons right now. I'll be with you shortly. How are things?
Times are okay.
It doesn't sound too
Some of the
optimistic.
stuff.
Say that again?
Having a bit of trouble with some of that spherical stuff.
Oh, okay. Then I guess
it's complicated.
It's a very visual geometric thing, so sometimes people find it a little bit easier to do, I guess. I'm not sure. I don't mind it so much, me personally, but that's just me personally. Other people, different.
I think most
because
of
it's
my
formulas.
problems with it stem from trying to find phi.
Right. Well, trust American to call it that. I call it phi, but I'm still going to call it phi, and you can still call it phi.
Phi, phi,
Phi, fo, fum. That's what I was thinking as well as you said that. But then I call it theta, and you lot call it theta, so go figure. That's me, I believe. So let's see if we can switch it around. So I guess what we'll do is we'll start with the spherical stuff, since that's certainly causing some issues, and then hopefully we'll have enough time to do some more of the changing variable stuff. Which is, this is still facing me, so I guess I need to go this way. It's like Justin's having problems getting in. Hi Rachel, how's things?
They're going good. I got a little stuck on the change in variables.
It's not a surprise. I think everybody, not everybody can ever say everything with everybody. A large number of you will probably end up getting stuck from time to time as well. That's the nature of the beast.
Thankfully, a lot of the density ones that require you to find the coordinates for the center of mass, they're all about the z-axis, so it's a 0, 0 for x and y.
Oh yeah, so you're using symmetry to get 2 out of the 3. Always look for symmetry. Yeah.
Hey, this is all the same. That means it's 0.
Well, if it's centered around the origin, going vertical upwards, yes. I mean, if it was centered somewhere else, it might be different. But as you're right, spherical coordinate systems are all based around the origin. Actually, cylindrical coordinates are pretty much always based around the origin is one of the axes, because it's like a cylinder going either vertical or one of the 2 horizontal directions. So
there was one question on there where it was actually scooted over or scooted up on the z-axis, but that didn't matter because it was still 0, 0 on x and y.
Yeah, because it's just a cylinder being moved vertically. It doesn't really change too much. Yeah, so in a way, you're right. That does help if you see it. If you didn't see it, you would eventually get the answer. I mean, the math would just come out, and you'd say, "Oh, it's 0." Come on, Justin, what's keeping you, poor guy? It looks like you're still trying to join. Going to have to start in a few moments. Oh, here we go. Justin's trying to do it again. Maybe that's his issue. Looks like we're all through. Perfect. Well, good morning, everyone. Guess again, I should say just good afternoon. By popular demand, we're going to look at some spherical stuff first, and there's a fair amount of geometry involved in it, and depends on whether you see things visually or not, whether that is going to be an advantage or a disadvantage to you. I forget that my brain is not the same as yours, and I find visual things a lot easier than some. I guess because my brain sees visually. You know that I move my hands around a lot. That's because I'm essentially, not scary thought, but I can actually internally visualize the shape. And so I'm moving my hands trying to say, this is what I can see in my brain. Just scary, I know, but it's just the way my brain works. So here we go. I'm just setting up something while we're waiting here. And, oh. And that's a different question. Okay, I think I'm almost ready to go. Right, I guess we should do the usual things first. Is there anybody who has any general questions before we get started? Your homework this week is pretty straightforward, right? It's just 3 sections and that's it. Next week, I know it's looking ahead, but next week we're only doing 2 sections, but we'll be doing a review quiz and a test, so it's probably going to be more work rather than less, right? If you can hear a thing at the background, it's I'm just printing out the attendance, because I found out a quick way to get participation points. I just do a screen grab of the list of your names and then I've got it. So that's cool. Right, so what you're seeing here is the idea that you can describe an object in 3D space, not just as X, Y, Z, Cartesian coordinates, but in what are called the spherical form. This funny thing that looks like a P, because that's how I write it, is called rho. It's a Greek letter, R-H-O, but you pronounce it like rho. You know this middle guy, he's theta. And theta, or as you Americans like to call it, theta, is the second one. And this third symbol that looks a bit like a 0 that somebody put a stroke through it, that's called phi. And I pronounce it phi, like in fee, fi, fo, fum, right? How did you pronounce it, Kawika? You pronounce it slightly differently from me.
Fee.
Say that again?
Fee. Like in
F,
fee, fi, fo, fum.
like fee. Right, so you say fee and I say phi, so they're pretty close. Right. It's a label. You call it anything you like, right? But they're the 3 guys. Now, I'm going to jump to a screen because there's no way in the world I would ever try and draw this. And this is me on the textbook. When you look at this picture over here, you can imagine this point P floating in the air in 3D space. The way you tell someone where it is on the XY plane, starting at the X and going in your usual you know, anti-clockwise direction, you get to this line. And then on this line, you then start on the ground, right? But it's a vertical axis, and you curve down the way, which is a bit unnatural, but you do. And the angle that you make with the z-axis is called phi. And the distance then that you project along that line gets you to the p. The closest analogy I've got is that if you look at the some maps, do you know you have latitude and longitude? Can you think of theta and phi as being like latitude and longitude? It's like that, right? Now, spherical coordinates are really good way of representing equations, x, y, z equations, in a much more concise form. But when those surfaces or shapes have a circular look to them in the most part, right? For instance, do you know a sphere will just be rho equals 5? All the points whose distance from the origin is 5 would get you the shell of a sphere, right? So if you said rho was between 0 and 5, haven't you now described a ball bearing in space, radius 5? So rho is very close to the r that you use in polar, right? It's telling you the distance from the origin to the point, right? Now, if you wanted to do a cone, you just need to say 0 to pi upon 2, and you're basically saying that phi is equal to c. So if you say phi is pi, God, what would you get? No, pi is a bad choice. If you said phi is pi upon 2 or pi upon 3 or pi upon 4, can you imagine a cone like this, or like this, or like this? Another interesting fact that it's very easy, and I almost forgot it myself, is do you know that rho has to be positive, which makes sense, the distance from the origin to a point. And do you know that phi must be between 0 and pi? Now you might think, well, how does that work? Well, if you're measuring z this way, and this is a positive z, that's 0. As you curve round, you get to pi, which would be vertically downwards. Do you know that entire movement covers the entire shape? Well, you say, but what about the back end? Well, do you notice how theta is going to circle round? If theta circles round while that other guy's doing his thing, do you see that you only need 0 to pi to get everywhere? Hopefully you can see that.
So it's a rotation about the z-axis.
Yes, it's a rotation about the z-axis, and you only need to go from vertically upwards, which is 0, to vertically downwards, which is pi. And if you rotate a shape, isn't that rotating everything you could possibly rotate? So, conversions. There is a lot of detail in this. You might want to get a hold of this. In fact, let me make your life a little bit easier. I'm going to make a note to myself to put these formula online. That's just so you'll have them in one place. But here goes. Suppose you want to convert from Cartesian to spherical or back at the way. If you know rho, theta, and phi, you just trust me. The x coordinate is rho, sine phi, cosine theta. The y coordinate is rho, sine phi, sine theta. And the z coordinate is rho, cosine phi. Right, so if I tell you it's 5, comma, a half pi, comma, a third pi, you see you just plug in halves and third pies everywhere that you see it, and whatever I said rho was 3, let's say I said that, you put it all together and you'll get answers like 5 root 2 over 3, 7 over root 2, and 15. You know, you'll get things like that. And that's how you would convert. So converting from polar to x, y, z, you use these 3. And let me just do an example of that question of this conversion to show you how it would work. So let's suppose I had a point and it's in polar it was 2 pi upon 4 pi upon 3, right? Now, that's the rho, that's the theta, that's the phi, right? If I want to get the x coordinate of that point, it's going to be rho sine phi cosine theta, which is going to be 2 times the sine of pi over 3 times the cosine of pi over 4. And that's going to get me 2. Okay, what's the y coordinate of pi upon 3? What's the sine?
That should be 1/2.
And then root 2 over 2. So the whole thing all comes out as root 2 upon 2. So root 2 upon 2.
Hold on. No. I was thinking of pi over 6.
Uh-oh.
It should be root 3 over 2.
Right, root 3 over 2. Quick fix. Root 6 over 2. Do the y coordinate. Rho sine phi, sine theta, 2 sine pi over 3 again, times the sine of pi upon 4, and by sheer coincidence, same guy. Typically, they will not be the same. Z is rho cosine of phi, which is 2 times the cosine of pi over 3, and the cosine of pi upon 3, we'll leave as a half then, you get 1. So are we comfortable that it is possible to convert from one to the other? It's not particularly difficult. It's just know your unit circles and hopefully make sure I've written down the right guys in the right place. Of course, you have to go the other way, don't you? Let's return to this question. The reverse process. How do you take Cartesian coordinates and turn them into polar? Much messier. Rho squared is this guy, which means that rho is the square root of this guy. A bit like r is the square root of x squared plus y squared, right? But in 3 dimensions, rho is the square root of x squared plus y squared plus z squared. So you can get rho pretty easily. Now, how do you get z? Well, if you take this expression here, do you see if you rearrange it, then isn't the cosine of this guy z over rho? Now, you know z, and you've already, I'm assuming, calculated rho. So you're going to be left with the cosine of phi is root 2 over 2, or a half, or something nice. And then from there, can't you get phi by doing the inverse cosine? So hopefully it's a nice angle, right? Something that's on a unit circle. It should be. Now, how do you get the cosine, or how do you get theta? Well, if you rearrange this formula, cosine of theta is this fella. You know that one. You just found that one. Now that you know this guy, shouldn't you be able to get that guy? And the sine of that guy is what you've got. Are we good?
Yep.
Right, so here's kind of one that I prepared earlier. Oh, good, I am recording, so that's good. 0, negative 6, 0. Right, can you imagine rho squaring everybody and getting 6? That's the cosine of phi, gets you 0, so that makes phi pi upon 2. You know, when is cosine 0? Pi upon 2. Cosine of theta is this ugly guy, which becomes this guy, which is 0. and this ends up being 3/2 pi. And the reason that it's this one and not that one is that, do you recognize that that y is negative? And so if you can imagine what that would look like on the y axis, isn't your guy down here somewhere? So you are looking at, oops, that fella, which is that guy, right? Actually, let's do that again. Is that guy, right? That isn't even us doing any integration yet. That's us just getting comfortable, or at least to get comfortable with how you would take Cartesian and spherical and jump between one and the other. When you put the whole package together, however, there is a formula that allows us to convert a Cartesian XYZ world into a rho phi theta world. And the formula is this guy here. Spherical only works on three triple integrals, right? It's three-dimensional thing. And suppose we have a function x, y, z, dv. dv is just short for dx, dy, dz. If you convert it into polar, you convert it into a triple integral. I'm just going to call this thing f, x, y, z, but actually the x's get replaced by this fella, the y's get replaced by this fella, and the z's get replaced by this fella, right? And you then have, over at the end here, d thingy, d thingy, d thingy. Now, when we did polar, didn't you have a funny little r, dr thing going on? In this case, you get an even messier thing. You get rho squared sine of phi. That is fixed. In fact, that whole thing is fixed. So what you're going to get, a kind of question that you typically might get is, find the triple integral of this region E. And this region E is maybe half a sphere or a cone. They're the most likely shapes, right? And you're going to convert it into its triple integral limits. The x, y, and z in your function, you know, your function might be x plus y or x squared plus y squared. Your function is going to get replaced here. And then you're going to finish with rho squared sine phi, and then you do the three variables, phi, theta, and rho, in any order you think is worthwhile. So far, so good?
So far.
It's one of those, just, you know, you got to do what you got to do. You got to just have a whole lot of formula. I've got an example of one here that I'm going to work on to kind of take you through the integral part, because that's, to me, much more interesting. Here is an example. It's question 8, which is quite far on.
Oh, that one.
You know this one, Kubika?
I know that one. That one was a bit tough.
Okay, so good choice then. We have a triple integral over some region B. The formula that we have here is x squared plus y squared plus z squared, all squared. Essentially dx, dy, dz. And the region that they're calling B is a ball, which I would call a sphere. But if you take a sphere and you fill its inside, I guess you could call it a sphere. And it's a ball, and its radius is 3, at least in my version. Okay, let's see what we got here. If you want to describe in 3D space a sphere, then you can do rho equals 0 to rho equals 3, right? That'll get you from the center of the sphere to its outside. You're going to do theta equals 0 to 2 pi, and you're going to do phi equals 0 to pi, like I described above, right? Z vertical is phi equals 0 all the way down to phi equals pi, right? So you have to kind of grab your paper and turn it sideways because it looks kind of weird if you don't. Now, this fella here is going to get replaced. Now, I could take the x, the y, and the z in the formula that I've got, square everything and add it, and 4 lines later simplify it. Or I could realize that x squared plus y squared plus z squared is rho squared. That makes sense for a lot of works. Right. Now, what do I tag on at the end? Well, I tag on all those extra bits. You're always going to have a rho squared. You're always going to have a sine phi. Then you're going to have a d rho, d theta, d phi going on, right? Remember, that's always there, right? So we're going to go from 0 to pi, from 0 to 2 pi, from 0 to 3. That guy squared gets you 4. That guy gets you another one, and you get 6 sine of phi. What's that? D rho, d theta, d phi.
The thing I like about this one is you can just split it up.
Exactly. Do you see that these are multiplied together? Right, there's no any, this bit plus that bit where the variables are different, right? You can split it. So you can split it as this guy, d rho. And since I didn't give myself enough room, I'm going to go in this direction. We all know that that's allowed. What do I know about theta? Doesn't appear, doesn't appear. So that means theta is just a 1 then. And what do I know about the last one? Well, I have a sine phi, and phi is 0 to pi d phi, and dot, 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 dot. Would you agree that from that point onwards, it's just number crunching?
The most important bit on that one is remembering when you go from sine phi and integrate, it becomes negative cosine phi.
Yes, you have your integration hat on. Correct. Are we okay with this? Now, spherical coordinate system is a very small niche market. You're only ever going to use it when the region that you're integrating, right, this thing they're calling B, is a sphere or a bit of a sphere or a cone, because those shapes, I guess ellipse maybe, but less ellipsoid, but less likely. Those are the kind of shapes that work well with spherical coordinate systems. Yeah, you're going to have this ugly guy. Hopefully the function that you're integrating, this fellow up here, hopefully he's not too nasty. Just an x on its own or an x squared plus y squared. And typically, you do have to, unless you get lucky, replace every x with this, every y with that, and every z with that. Now, can you imagine this question was the same question with one difference? It wasn't this guy. It was just z. Right? So it was the same ball, but not this, but z. This chunk here and this chunk here, totally untouched. The only thing that would happen is that the z would get replaced by a rho cosine phi. And then you split it up into little bits and get the same kind of result. Are we good?
Yep.
Right. Now, before we move on from spherical then, because I guess it took longer, but that's fine. Is there any other examples, homework in the spherical that you might want me to do? And then we'll move on to the change of variable stuff.
Number 15 I had a bit of trouble with.
Okay, let's have a look at 15. No. See what my version of 15 is. It might not be quite yours. Okay, so essentially you've got a between. I know that's not the phrasing, but I'm using that as my phrasing. And you've got an x squared plus y squared plus z squared. Looks like in my case it's 25, but it may be 36 or 49 in your example. And then we've got a cone. I believe it's a cone. Yeah. And it's a cone, and it's the square root of what, x squared plus y squared. Are we comfortable with that part of the puzzle, right?
Yep.
So what we're going to have to do here is I'm going to rearrange this guy and call it z squared equals x squared plus y squared. So far, so good. Now, if I put these together, what I'm basically doing is I'm trying to find out where this sphere and this cone kind of interact with each other. So I'm trying to find out when this and this kind of match up. And if I do that matching up, I believe I get 2x squared plus 2y squared equals 25, which is what x squared plus y squared is 25 over 2. Are you happy with that? Now, what does that tell me? Well, doesn't that tell me that the xy plane, we're basically just looking at a circle? Isn't that x squared plus y squared 25 over 2 on the xy plane look like a circle? So it tells me that this cone and the sphere, when they meet up together, if you looked at it from above, what you would see is a circle. What does that help me do? Well, it tells me quite a lot here. It gives me my theta equals 0 to theta equals 2 pi. Now, if we call these two guys, oops, this guy here and this guy here, if we rearrange these guys, in what we've got here is basically a sphere. And this fella here is our cone. Losing place. Right. I'm going to cheat a little bit here. I'm actually going to cheat a lot here because this question will take me about 15 minutes because I know where it's going. Because I'm going to have to set up my limits integration of the other two. I'm then going to have this guy first, take away that guy second, and then I'm going to have my rho squared d rho d phi d theta thing, and then I'm going to have to plug in some integrals, and the limits integration are going to have rhos and phi's in them as well, and that is not a pretty question.
I think that one was also below the cone, so.
Oh, so I may have to change my angles. I didn't pay enough attention to that. So.
That's the phi angles.
Right, okay. So what we got here is that x squared plus y squared plus z squared equals 25. Isn't that just another way of saying rho squared is 25, which means rho is 25? You're comfortable about
So rho is 5?
that rho is, whoops, that rho is 5, positive because it always is. Now, if you take the cone that z equals square root of x squared plus y squared, that's going to take a little bit more work, so I'm cheating here. And phi ends up being, in this case, pi upon 4. Now, how are you going to do that? Replace the x and the y by their spherical values, square them, add them, take the square root, and you'll find out that you get a cosine equal to root 2 over 2, which gives you the angle pi upon 4. So you're going to just trust me that that guy ends up being generated by this fella. That guy there ends up being generated by that guy. And when I put all my pieces together here then, that's my theta, That's going to be my phi's, and these are going to be my rho's. Now, since rho is 5, and I'm going from 0 to 5, this is pi upon 4, which is going to go here. What's the maximum value that phi is allowed to be?
Pi over 2.
Yeah, pi. In this case, pi over 2. Sorry. You're right, it is pi, but in this case, it's pi upon 2 because I think you mentioned it was above or below the thing. Right, so I'm assuming that pi upon 2 gets me the below half, and 0 to pi upon 4 would have got me the top half. That's a bit vague. Right, what else have I got? Then all you do then is that you plug in your rho squared, your sine of phi, and I don't have room for the drd thing to phi, but that's the guy. Because if you find the limits of integration and you want to find the volume of something, isn't the volume the triple integral of 1? It's essentially 1. And that's how you would do it. I'm not convinced that was a very good explanation, but
That made sense.
if it made sense, it might be something you have to kind of dwell on for a while, right? And, you know, think about it and mull over it, whatever. Right, let's see if we can get back here. Okay, can we move on now to change of variable?
Yes.
Right. We've done at least 2 days of changing variable, and I still feel like I've only touched on some of the topics. We haven't really got to any of the later ones. So the real questions, to me, the real questions don't begin until question 9, which is roughly halfway. But the ones at the end are going to take a long time. Another thing that's driving me crazy, and if I ever meet the guy who is the author to this book, I will tell them. Jacobian, you know the guy, right? We talked about him. And I said he is always positive, and he is. And I'm still not changing my mind because he is. You can do a calculation, right? And I'm making up numbers here because I want to. And negative 28, take away 3 is negative 31. But Jacobian should be positive, so we call the answer 31, right? I am still not going to change my mind. I am right and they are wrong. They are making a difference between this notation and this notation. And so they ask you in the book to give you that. But you know when you do your double integral, aren't you going to have to use that anyway? And I don't like that because the fact that you do that is going to make you sometimes forget that you need to change the thing into a positive value. If you do a test question and you end up calling that 31, when I do a check of your working, in fact, even if you don't do it as you're working, I will fix it and you will get the full points for that. Because to me, if you called that 31, I think that's a better answer than negative 31. So, okay, we may be nitpicking that that's got the absolute value and that doesn't, but I don't think it's a good idea to even think about doing it this way, right? So to keep the book happy and so that you get the right answer in your homework, will you stick negative 31 in for those questions where the number is negative, but will you remember to do positive value inside your integral, which it probably should have been right at the start. I'm going to complain to the guy when I get a chance. Has anybody want to pick a particular question and we will just go for it and have a shot at it?
Number 6.
Well, that's earlier than I thought. I wonder what's up with 6. Oh, it's find a Jacobian. Okay, that's not going to be too big a problem, I think. we have got x is equal to, at least in my version, 3e to the s plus t. Actually, I put a PDF of this same question or similar to it in Canvas, so if you go back and look at it, you can actually see it. Right. My s's look very like 5, so I'll try and make them less so. Let's do the Jacobian. Since it doesn't have the absolute value around it, we'll stick to their notation. Right. Differentiate with respect to u, differentiate x with respect to v, differentiate y with respect to u, differentiate y with respect to v. Okay, if you differentiate 3e to the s plus t with respect to s, you just get 3e to the s plus t. Let's do that as a side issue. If I went and said to you, y was e to the 5 plus t, and I asked you to differentiate it with respect to t, wouldn't the answer be 5 plus t? Agree? Now, if you stick a 3 in the front of it, it's still 3 e to the 5 plus t. Isn't the 5 an s? Right. And I've just realized that I wasn't paying attention as me, because it's s's and t's, not u's and v's. Right. If you differentiate this guy, you also get 3 to the s plus t. If you differentiate this guy with respect, let's just write it again. So the top two, the derivative just looks like the original. So does this one. What happens if you differentiate this fella with respect to t?
It becomes negative.
Yeah.
Although the first differentiation of the y to the s should have a 5, and it should be s minus t.
Thank you. Right. Now, major diagonal. This fella times this fella. Subtract. Minor diagonal. Now the rest is algebra. 3 times negative 5 is negative 15. If you multiply 2 powers of e, you add their powers together. Negative 15. You add their powers together. But in this case, the t's cancel out and you're left with 2s. And you're left with another 2s. Which means you're left with that guy. And to keep the homework computer happy, negative 30e to the 2s. But when you stick that guy inside your triple integral, when you do the change of variable, will you remember to turn it into positive 30e to the 2s, or else your integral will be wrong. Right? I know it was kind of thinking too many steps ahead and screwing up the notation, but are you comfortable with the process and where that came from?
Yeah.
We good? Okay, so where are we off to next? What's our next question?
Can we do 14?
All right. So let's have a look at 14. That is well on the way, so that should be a nice, scary question. Oh, it's the last one. So it should be scary, right? So we're doing in question 14 a double integral of a region R. In my question, it has 9 x add y e to the power of x squared minus y squared. dA, I'm just going to call that dx dy because that's all it's a code for. And they have given you the range is x minus y equals 0. X minus y is 6. X plus y equals 0. And x plus y equals 9. And that's it. And they start off by throwing you right in at the deep end. And they say, hey guys, we need a U and a V sub. And you're looking at that and thinking, who is my U and who is my V sub going to be? Well, there's lots of clues. These are the major clues. Because if I make U x take away y and I make V x add y, won't these double integrals just turn into U equals 0 to 6 and V equals 0 to 9? So you see why I chose the U and the V that I chose. I used the limits of integration restrictions that they gave me on this region. And I said, oh, these two guys are both the same. They just have 0 and 6 at the end. And these two guys are both the same. They have 0 and 9 at the end. If you ever see that, there's a very, very good chance that the first equation is your U and the second equation is your V. Are we good so far?
Yes.
Yeah.
Right. Now, since I've got this fella, I'll try to be more careful because I know what I'm like. And I'm going to find the Jacobian. And I'm going to find the whole thing, right? So here goes. Oh, God. This is scary because it's so easy I'm going to screw up. If you differentiate this with respect to x, you get 1. And this guy, you get -1. This guy, you get 1. This guy, you get 1. The major diagonal is 1 times 1. Take away 1 times -1. The answer is 2. And I don't need to worry about it because it's positive 2, so that ain't going to be an issue. So that means that my Jacobian fella, oops, that guy in there, start the next line, 0 to 9, 0 to 6, is going to just be 2 times du dv. So who's left? Let's focus on the f of xy guy. You see that 9x plus y e to the x squared minus y squared guy?
I have a question about the Jacobian.
Yes.
Do we not solve for x and y and then find the partials with of x and y with respect to u?
God, yes.
That is what we do. Okay.
It's what we do. Can I tell you the answer is going to be a half?
Yes.
Okay. That saves me having to redo it.
All right.
I just, yeah, we have to solve for that. Once I've finished this, I'll come back to that and prove to you it's a half. Right. Now, I have 9. X plus y gets me u. What will x squared minus y squared get me?
UV.
Isn't it? Yeah, uv. Isn't it x plus y times x minus y? So it's essentially uv.
Mm.
Now, at this point here, we've converted it. Okay, there's some tidying up to do. Right. But this integral You can switch the order if you like, because they're both numbers. If you took care of the U first, it might make it a little bit easier. I'm not sure it would. But you know you're going to have to do an integration by parts, and that's going to take you another 5-10 minutes. But you will eventually get the answer. You trust me on that? You will be able to do that.
Yes.
Right. Now, let's go back to getting the Jacobian back to front and upside down. It was too easy. I should have known it was too easy. I need to find out what the thing is. No, let's do it in a separate paper. I need to find out what the thing is, x in function is in terms of u and v. So I know that u is x minus y, and I know that v is x plus y. And I think solving system of equations, if I add these two equations together, I get that. Agreed?
Mhm.
And then if I divide everybody by 2, so that's what x is equal to. You happy about the process? It's like solving a system of equations, but there aren't any numbers now, right? You're trying to find out what x is, but instead of being 4, it's now a combination of u's and v's. And now that I know this one, can't I go back to, oh, say, equation 2? And that means v is equal to a half u plus a half v add y, which means that a half v, what's that going to be? A half v minus a half u. That's what y is going to be.
Mhm.
Now, if I then go back and do my correct Jacobian, try not to screw up here. This guy gets you a half, this guy gets you a half, this guy here gets you negative a half, and this guy here gets you a half. And so you get a quarter, take away a quarter, there you get the answer a half.
Mhm.
Okay. Now, do you want to see a cheat?
Yes.
Sure.
Yes. How did I know that even although I screwed up and I did it with the x's and the x's and the y's instead of the u's and the v's, how did I know that this guy became that guy? This is the cheat.
Are the functions inverses?
Yes. So essentially, if you do the Jacobian the wrong way around and it's linear, 1 over that answer will be the Jacobian of the one you were trying to get.
Ah.
As long as it's linear, right? A big, big constraint, right? But as long as it's u equals 2x plus 4y and v equals 6x minus 10y, you know, that kind of thing?
Mhm.
You can get the Jacobian the wrong way round and then just take its reciprocal and it will be the Jacobian of the right way round. Does that make sense the way I phrased that?
Yes.
Right. So I don't know how many linear Jacobians were out there. It might only be 2 of them, but I guess, you know, for the 5 minutes you spare, you do it. You sometimes can't avoid having to do it the right way around, because in this particular case, wasn't the limits for u and v already handed to me on a plate?
Yep.
Mhm.
Sometimes don't you have to draw the darn picture of what the new guy looks like to find out who the u's and v's are? In that case, there is no advantage of doing the shortcut, because you still have to find out what x is equal to in terms of u and v and what y is in terms of u and v anyway. So you just have to do it. I know I've kind of on the end of your time limit, but so if you have things to do and I don't want to, and your time's valuable, I'll let you just go. But otherwise, I'm just going to hang in here and you know, do another question or two until you feel you've had as much help as you want, and then we'll close it.
Well, speaking of drawing the damn thing, could you show us an example of that?
I will. Let me show you an example of that right now. Take me a few seconds, so hold on. I am doing stuff. It just It's a matter of hitting a lot of buttons. Right now I'm going into Canvas and I'm loading up Canvas, our page. It's taking forever to load up. There we go. I think I put it here. Okay. In here. Okay. Looks like
That'll help with the first couple of questions in the homework.
Gotcha. Okay, here we are. And I'm going to have to go out before I can go in. Darn it. Ha! It's fighting me. Doesn't want me to get out. Okay, I'm in again. Right, I'm going to share the screen and show you one that I've already done, and then we could maybe pick another one if that's something that you'd find useful. Here we go. Right, you should be looking at this screen here, chapter 15, that's got the videos and the notes in it. Are you seeing that? Right. If you scroll down to the bottom, there's a section called PDF files. And what I've done is I put a couple of PDFs here. This is the one where we're going to look at how do you get the darn region, right? So, do you notice those questions where they describe the region by giving you typically 4 points? The coordinates of 4 points. So in this question here, I wonder if I can make this even bigger. There. In this question here, the 4 points of these coordinates, and X is this guy and Y is that guy. Well, that's good that they've gave me X and Y in this format, because I really need this format. Won't I be able to do my Jacobian without any trouble? Right. Now, this is what the region looks like in the XY world. So if we jump to what does it look like if you draw it? It looks a bit like a parallelogram or a rectangle on its side. Now, that's the XY world. How do you convert it to the UV world? Well, U is X minus Y and V is 2X plus Y. How did I do that? I went here and I solved in a similar kind of way that we did the other way around, and I found out what U was equal to and what V was equal to, right? It's a bit like add equation 1 to equation 2, cancel things out, right? Same process. So if you can trust me that U ends up being X minus Y and V ends up being 2X plus Y. So no matter how they give you the information, you probably are going to have to know what the other one is. So if somebody says X equals this and Y equals that, that's great. But you're probably still going to need to know what U equals and what V equals. So what I'm doing is, see these 4 points, these coordinates? I'm going to find out where they move to. So for instance, the point negative 3, 6, which is the XY coordinate, turns into the UV guy negative 9, 0. I'll show you how that works. If you go up here and you make X negative 3 and Y equals 6, negative 3 take away 6, negative 9. And then if you go 2 lots of negative 3 add 6, you get 0. So you can see how this point gets transformed to this coordinate. And then you do it to the others, and guess what? You get a pretty little squares come rectangle-y thing, right? Now, what's the usefulness? Well, can you see that the U's go from negative 99 and the V's go from negative 99? And so I now have all the pieces. I know my limits of integration.
Would they go from 0 to 9?
Yes, they do. I screwed up.
Okay, yeah, I see how it goes now.
Yeah. Note to self, fix that. Right. apart from the fact that I don't know where -9, 0 should be plotted. And that's going to be an easy fix. You know, I'm just going to drop this blue line down here. But it does mean I'm going to have to change these to 0 to 9. But that's essentially an example of that picture being drawn. Here's another one. This is question 10. Here are the 4 points. I think this time, yes, I did them in the right place. That's a weird shape in the XY plane. If you solve the transformation stuff, rewind. Choose an appropriate change of variable. Now, in this question, you've got nothing here to help you. They're just coordinates. And there's not a lot going on here. But y minus x over y plus x, they're the only two guys in town. So I'm going to make u y minus x. I'm going to make v y plus x. Does that seem a reasonable assumption if there's nothing else to play with?
Legit.
That's the two guys I'm going to use. Now, this is what the region looks like. That's what those 4 points make, or some kind of weird trapezoid, I should say. That guy. If you solve, actually, I don't need to solve this time. They're already written the way I want it. If you plug in the x's and y's and you solve for them, you get these guys. And the space ends up looking like this, which might look just as bad as that, but it's actually quite useful. Because in this case, the u goes from negative to plus. That's the equations. This is u equals v, u equals negative v. And the v's go from that point there, which is 7, to that point there is 8. And then you go and you do a whole load of integrals. And this one works because I checked it with the solution, so I didn't screw up on this one. But you can look at this in your own details. It's already kind of online for you. So take the 4 corners, take the formula for x equals and y equals and whatever you've got, use it to transform the thing, and the new shape will allow you to decide what the u's and v's are going to be. In this case, one of them's a number and the other is a function of the other. So has anybody got a question maybe to create another picture, or do you want me to do an example of one last change in variable? Yeah.
Does question 4 create a picture?
We can go there. Got in 4. What have I got in 4? Okay. Question 4 does not have a draw the shape, but that's fine. It doesn't need to. We've been asked to find a double integral on some region R. The version I've got has 8 lots of x take away 8y over 6x take away y, and we'll just call that dx dy. And the region R is described in a pretty standard kind of way. It's from x minus 8y equals 0 to x minus 8y equals 2. And then it goes on and it says 6x take away y is equal to 1, and 6x take away y equals 2, or at least a version of
using
that.
these then.
But yeah, we do, don't we? Okay. I know you know it, Kimika, so I'll ask you not to jump in yet. Give everybody a few seconds to think about this. Based on what you can see in front of you, there's only one candidate for the U and the V, right? Anybody else apart from poor Kimika? Just so we can have some variety.
U equals x minus 8y.
And V?
V is 6x minus y.
And do you see it comes from here and here?
Yes.
Right. That was Guaranteed. That's what you were going to say, Kawika, wasn't it?
Yep.
Yep. Okay. Now, we got to be able to look at this guy, right? And we got to be able to figure out what that information is telling us. It's telling us quite a lot, isn't it? Isn't it telling us U goes from 0 to 2? And it's telling us that V goes from, what, 1 to 2? Won't this guy still be 8? Won't this guy be a U? Won't this guy be a V? I've still the Jacobian to get du dv. Can you see this question's almost done?
Yes.
But to get the Jacobian, don't we have to take these two equations and rewrite them so that x is in terms of u and v and y is in terms of u and v? So let's do that guy at the side. Now, this one is messier than many, because in lots of the questions you can get away with the first equation, add the second, or the first equation, take away the second. Can you see in this case, neither of those are going to work? Don't you have to do a little bit more to make them work?
Yeah, that's where I got really stuck.
Okay, let's look at it. Pretend that that guy was 7 and that guy was 10. Just pretend. If these two were numbers, right? Wouldn't you try and arrange the equations so that one of them had the same number of x's as the other, but it was a positive and a negative number of x's? Or one of them had the same number of y's as the other, but one was plus and one was negative, right? Let's do the same thing. I'm going to make this guy plus 8y so that he can kill off this one. Now, to make that plus 8y, I'm going to multiply everybody by negative 8. So the first equation, I'm just not going to do anything to. And the second equation, I'm going to multiply by negative 8. Now, when I add these equations together, oh, God in Himmel. God, that is ugly.
Yeah, that's very ugly.
All right, well, it is what it is. You have to trust the math. Negative 147u plus 847v equals x. And I can see myself talking myself out of that right answer by saying it can't be that ugly, but evidently it is.
Okay.
Right. Now, once you got x, can't you plug it in and get y?
Yeah.
And then this Jacobian up here is going to be a number, right?
Mm-hmm.
Oh, by the way, is this guy a candidate for the cheat?
Yes.
He is.
Yeah, should be.
So can you just not even worry about this?
Yeah, and then inverse, right?
And then if the answer's 4/3, make it 3/4.
That makes it easier. Thank you.
Bam, cheat.
Well, cheat.
Shortcut.
I don't know what you want to call it. It's. I don't know if you ever had me. Did you ever do in Calc 2 a thing called the cover-up method?
Yes, I remember
that,
teaching us that.
You know that's a cheat in the sense that it's a quick way to get the answer, but the foundations of why it works is a bit shaky.
I didn't know how to do it the right way in order to take a shortcut.
Right. So can you can do it the long way and find out the answer. But and by the way, these are all linear. That's why I get away with that. If there's an x squared plus a y squared in there, forget it. You got to do it the hard way, right?
As far as taking shortcuts go, knowing how to get there is part of the big thing.
Yeah, it is. And it's, hey, you'll get the answer, right? It won't matter. At the end of the day, you will get that answer. So that is good.
Especially on tests.
Yeah, when time is a prisoner, right? You don't want any of it to get away. You probably want to try and use some shortcuts if you see them. Right. For a faint moment there, Christopher, I thought you died on me, but then your head moved, so I know you're still alive. So you were focusing a lot on that question. A little side issue. Let me just, in case you're not 100% sure what I mean by the cheat or the shortcut. Let's suppose that was our U and our V. Now, we know that we want to find this fella. But that would involve us having to convert this into x equals and y equals. And it's probably going to be an equally -1/37 or something really messy. The shortcut says to do that guy. So what's that going to be? It's going to be a 1, a -3, a 10, a 7. 1 times 7 is 7. Take away a -30 is add 30. The answer is 37. But won't our Jacobian just be 1/37?
Yep.
So that's what I mean by the cheat, right? But if they ever do this to you, don't use the cheat.
Really can't at that point.
You'll get a number. I'm not saying you won't get a number. It just won't be. Well, actually, you won't get a number. You'll get X's and Y's, which isn't much help because your Jacobian has to be U's and V's. So that's the first reason not to do it. You might be able to, if you work really hard on it, turn the X's and Y's into U's and V's. But trust me, even that won't work because it won't be the right answer anyway. Analogy. Remember when we did the cover-up method? It's only good for linear. It's only good for 4x plus 1 over x minus 2 times x minus 3, those kind of things. If there's an x squared minus 2 in the bottom, the shortcut, the cover-up method doesn't work. I'm willing to keep going, but I really don't want to make you feel obliged that you need to keep going. So what's the feeling here? Do you want me to do some more, or do you want to get on and start doing it yourself now?
I think that covered the basics of everything I was looking at.
Okay, so you sound like you're good. Anybody got a question they might want to ask, in which case go ahead and the rest can leave or listen to that person's question.
All right, thanks a lot. Yeah, I have to roll, but I appreciate it.
Okay. Thank you for hanging about even longer than you were expected to.
I don't mind. I got a lot more information that I needed for this homework, so.
Okay, you got more than you needed. That's better than not enough. Right. I'll wait a few seconds more.
See you next week.
See you next week. Bye-bye. You're good, Rachel?
Yeah, I think so.
Okay. You have fun. If you have any issues because you don't know what you don't know until you hit a question, shoot me an email and I'll see if I can help you that way.
Thank you.
Okay.
Professor, I had a
Yes.
question.
Go for it. What you got for us?
Okay, so going back to the spherical coordinate.
Okay. Let me find my set of questions on spherical. That's not it. I got it. Right. Is that a question or just an idea? What?
If you could really quick explain again how you go to finding, like, when they don't give you phi and you have to find phi instead, like you have to convert from.
All right, so the two versions of this question, is it the early questions where they want you to convert a Cartesian into a spherical, or is it the later questions where you are given two regions and you need to find out what the limits of integration are in terms of thetas and phis and so on?
The second one.
Second, okay, so we need to find maybe a question where I can use that as a way of doing it.
Is it just?
Yeah. You were going to say something? Is it just?
Yeah. Is it just cos inverse or?
Oh yeah, right. Okay. Can you imagine you did a whole load of work and you got to cosine of phi is a half, right?
Right.
And to get phi, you use, as you were going to say, I think I heard you say it, that guy.
Yeah.
Now, when you do the inverse cosine, you typically get one answer in the first quadrant in this case, right?
Yes.
Right, and so you're looking for an angle whose cosine is a half. So basically, you're looking for an x-coordinate, aren't you?
Yes.
Right, and if you imagine this is your unit circle, and the guy you're looking for is probably here. Oh, wait a minute, yeah, its x-coordinate is there, right? So the answer you would get in this case would be pi upon 3. Now, you might say, but wait a minute, there's another angle down here that could have worked, right? There's a restriction. The phi is always between 0 and pi.
Okay.
So when you're looking at it that way, to give you another example, suppose phi was, the cosine of phi ended up being saying negative a half. Then phi is going to be the inverse cosine of negative a half. And the negative a half guy is over here.
Right.
So the phi you would get would be 3/4 pi, which, no, 3/4, 2/3 pi. But that's okay, because he's still in that thing.
Right.
Right, so if that was your question, yes, that's how you do it. Now, if it's the sine of theta equals a half, or the sine of theta equals negative a half, that kind of thing, theta is allowed to be between 0 and 2 pi. So that could mean that there are two distinct values of theta in that situation.
Oh.
Right?
Okay.
So
Yeah.
you might want to look at some other clues in the question. It might, for instance, say it's only above the XY plane, or it's only below the XY plane, or some other thing, so you can figure out which of the two choices, because it has to be one, you're going to use.
Okay. But if you're given X, Y, and Z, and you need to find rho, phi, and theta, so I thought I was listening, but I can't. I don't know.
Okay, I'm going to do an example of one of these questions from the start. I'm going to apologize right now that the numbers I'm going to pick won't come out pretty, because it's very hard to pick numbers that are going to come out pretty, but I'll try my best. So let's suppose we had a guy whose coordinates were 1, 2, -2.
Okay.
Then that obviously is the X, that's the Y, and that's the Z. To get the rho, it's easy. It's simply applying this formula.
Right, okay.
So in this case, it's going to be 1, oh, I got lucky, but really I just got lucky. It ends up being 3.
Okay.
Right, we're good. You then move on and you use this relationship.
Okay.
Now, Z is -2, right? And rho is 3. So I'm going to have to just find the inverse cosine of -2/3. Now, can you pretend that that guy there was a nice inverse cosine function?
Yes.
It's a half, it's a √2/2, it's a √3/2, because that's typically what you are going to get, right?
Okay.
So can you pretend it was that? And if it was that, you'd be saying pi upon 3, or since it's negative, more likely 2/3 pi, right? You'd say something like that. Right.
Yeah.
Now, let's assume that we already have done that. Now, the last guy in the list then is the relationship that the cosine of theta is the x-coordinate over rho times the sine of this guy. Now, the x-coordinate is 1. The rho is 3. And since I know this guy, it's going to be the sine of 2/3 pi. Now, the sine of 2/3 pi, you would get that, and you look at your unit circle, and the sine of the 2/3 pi, I believe, is √3/2. And then you kind of make this look pretty. You probably would make it look even prettier. And that would be your last guy. So in polar form, it would be 3. Oh, darn it. I've forgotten what our quest was. That's all I know right now. Won't I take the inverse cosine of that guy.
Yeah, right.
Right.
Okay.
So my answer would be 3 because that was nice.
Uh-huh.
The phi was, I pretended it was 2/3 pi. And can we pretend that this one's a quarter pi? I know it's not.
Yeah. Okay. I see now.
Right. So you have to do it in the order rho first, cosine phi so you can get phi second,
Okay.
cosine theta so that you can get theta last.
All right.
But the order is rho, theta, phi.
Yeah. Okay.
So first, second, third.
Okay. All right. Thank you. That helps
You are
me
welcome.
a lot.
Right, you know how you contact me if you get stuck later on.
Yep.
Okay. Well,
All right.
bye-bye then.
Bye. Have a good one.
You too.